Okay, so in this video, what I'd like to do is move on with another example of a non-homogenous second-order differential equation, where we have d2x by dt squared plus dx by dt plus x equals e to the minus 2. So, first of all, let's just convert that to our standard Laplace notation. So we're going to have x double dot plus x dot plus x equals e to the minus 2. Yep. And then we can just remind ourselves of the standard Laplace notation. The Laplace transform of x we're going to call x bar. The Laplace transform of the first derivative of x will be sx bar minus x naught. And the Laplace transform of the second derivative will be s squared x bar minus sx naught minus x1. So again, we're going to take the Laplace transform of the left and the right-hand side. Using the principle of linearity, we're going to separate the variables and use these substitutions, which I'm going to do immediately. So we're going to end up with s squared x bar minus sx naught minus x1 plus sx bar minus x naught plus x bar equals 1 on s plus 1. And I've just taken the Laplace transform of all those things. We're also told that the initial conditions are such that when t equals 0, x equals 0, and dx by dt equals 1. So we can say that the x0 equals 0 and x1 equals 1. So let's substitute those conditions into what we have. So we're going to end up with s squared x bar minus s times 0 minus x1, which is 1, plus sx bar minus 0 plus x bar equals 1 on s plus 1. Yep. And I'm just going to take out the x bar, so we'll have s squared plus s plus 1 minus 1 equals 1 on s plus 1. So now I'm going to take the minus 1 to the other side. I'm going to say x bar, s squared plus s plus 1 equals, now if I take 1 to the other side, and plus 1, I'm going to do s plus 1 on s plus 1. And s plus 1 on s plus 1 plus 1 on s plus 1 is going to be s plus 2 on s plus 1. Yeah? And I'm going to divide both sides by s squared plus s plus 1. Again, we have here a non-reducible quadratic factor. So this is going to go to x bar equals s plus 2 on s plus 1 times s squared plus s plus 1. And now we revert to partial fractions. So that's going to be a on s plus 1 plus bs plus c on s squared plus s plus 1. And now we have to find those coefficients. So now we have the coefficients, and let's plug that back in. So we can say that x bar equals a 1 on s plus 1 minus bs s minus 1 on s squared plus s plus 1. So that works out as minus s minus b, and minus minus 1 works out as positive c as well. So this is fine. And now what we want to do is complete the square in the denominator. So we can say that s squared plus s plus a quarter minus a quarter plus 1, and that will go to s plus a half squared plus 3 on 4. I believe that is correct. So we just completed the square of this, and we're going to bring that back in. So we can say move this up. So we can now say x bar equals 1 on s plus 1 minus s minus 1 all on s plus a half squared plus root 3 on 2 squared. And the reason I'm doing it in that format is because I want something that's going to look like something that's familiar in the Laplace forward transform, an s squared plus an a squared. So it's exactly the same thing. I just square that, root 3 on 2, you end up with 3 on 4. Same thing. And I want to try and get this. This is the easy bit here. We know what that is. This part here, we want to get into something familiar. So we've got like a shift going on over here, s plus a half. So I'd like to put an s plus a half over here as well. So let's go ahead and do that. X bar equals 1 on s plus 1 minus s plus a half. Well, I need to subtract the half and then subtract the 1. So I'm going to be left with minus 3 on 2. Yeah, so a half minus 1.5 gives you minus 1. That's fine. Over s plus a half squared plus root 3 on 2 squared. And again, the reason why I'm trying to get this into this kind of format is because I want something that's going to look like an s on s squared plus a squared, because I know that's cosine, or an a on s squared plus a squared, which is the sine, or something like, even an s on s squared minus a squared, which would be the hyperbolic shine, or the a on s squared minus a squared, that would be the shine. S on s squared minus a squared would be cosh, something like that. And at the moment, again, what we're going to do, we're going to just separate these variables over here, which you can probably guess by now. So we've got the x bar equals 1 on s plus 1 minus s plus a half on s plus a half, and this is looking good, plus root 3 on 2 squared. That bit looking really good because we've got the same thing going on here and here, just with the square. And then we're going to have the minus minus, that's going to be the plus 3 over 2, all on s plus a half squared plus root 3 on 2 squared. So this is looking really good. This is looking excellent. That's looking excellent. This is looking not so good. And the reason it's almost good, but it's not quite, because we want the format of a on s squared plus a squared. So what we need to do is we would like to have root 3 on 2 sitting over here. So if we do, I'm going to do it in full, 3 over 2, 3 on 2, divided by what we want it to look like, which is root 3 on 2. That's going to be 3 on 2 dot 2 on root 3, which is going to be 3 on root 3, which equals root 3. So basically, if we multiply root 3 on 2 by root 3, we'll end up with 3 on 2. So what I'm going to do, I'm going to just kind of cross this out a little bit, you still see it, and I'm going to stick in a root 3 on 2, because I really want root 3 on 2 there. That's what I really want. That's perfect. And to make that really 3 on 2, I'm just going to multiply that by root 3 over here in front, root 3. Okay? So if I do root 3 times root 3 on 2, I'm going to end up with 3 on 2, which is what it really is. But I need it to look like root 3 on 2 over here. Because then I can do a on s squared plus a squared, which is sine at. So now that I've done that, I can now go on and say, and actually do the inverse Laplace transform, if we've got any paper left, that is. Yeah. Okay, so we can say now that x equals e to the minus t, which is from here to here, minus, now again, ignore the shift at the beginning. We've got s on s squared plus a squared. Well, that's the transform of cosine at, cosine root 3 on 2t, isn't it? With the shift, we're going to have e to the minus half t. So that's going to be e to the minus half t cosine root 3 on 2t plus root 3 times, and we've got an a on s squared plus a squared. Well, that's sine, isn't it? Sine at, but we've got the shift going on. We've got f of s plus a transform. So that's going to be e to the minus half t cosine, sine root 3 on 2 t. And that's our final answer. And I hope that was clear about why the shift is e to the minus half t. If it's not, look at the video previously because we covered that in a little bit more detail there. So there, it's final answer. X equals e to the minus t minus e to the minus half t cosine root 3 on 2t plus root 3 e to the minus half t sine root 3 on 2t, which is damped harmonic motion.